Hey, this is Presh Talwalkar. In this video, I will present 6 impossible puzzles with outside-the-box solutions. How many can you solve?
I'm a software engineer with 20 years experience doing private tuition. Let's see how many of these I can answer.
Puzzle 1. Here is a maze. You have to go from start to end, but there is a rule. You cannot pass through the same color door 2 times in a row. That is, you have to alternate between blue and red doors. Can you figure it out?
Okay, so we've got this maze. We're going to get from the start to the end. And those red and blue lines are doors. We can't go through the same color door twice. And that's all the information that we're given. Let's see if I can do it. Here's the question on a whiteboard. Let's see if I can figure it out. So we're going to go through a blue door first. Now we have to go through a red door. So if we go this way, then we have to go through a blue door, and then a red door, and I think we're trapped in this loop. Blue, red, it's going to keep going round and round. So I'm going to take that all the way back to here. We've gone through this blue door. So next we need a red door. We've tried the one red door, let's try the other one. Now we're here, we've gone through a red door, the next one needs to be blue. We've gone through a blue door, the next one needs to be red. The only red is that one line on its own. But I think that's useful because it allows us to flip and go back the way we came. So if we go through this red, it allows us to go back through this blue, through this red, through this blue, and then we can end up at the end of the maze. I think we've got it. The key here was using that single red door, which allows us to circle back and return along the same path. Okay, let's see what the actual answer was.
I want to give you a big hint.
Okay, he gives us a hint. You can go through the same door or enter the same room more than once. I think that's what we've done. We've gone through many doors twice and many sections, many rooms more than once. Let's keep going and see what he says.
Can go through the same door or enter the same room more than once. The only stipulation in the puzzle is you have to alternate between doors of different colors. So how can you do it? Rather than just show you the solution, I want to show you how you can solve the solution by thinking through it logically. So here's
I've just noticed, I think the best way of doing this is to actually work backwards. So starting from the end and working backwards, following different paths. Let's see. Let's see what
general approach. Let's start out by considering each different area as a different room. So at the very beginning, we are starting out. So let's call this room number 1. We enter the first area and we'll call that room number 2. We can call this area room 3. Let's call this area room 4, this room 5, this room 6. Here we have room 7. And finally, when we exit, that can be one more room, which we will call 8. So we have 8 different areas of this maze. So how do we get from 1 to 8? We need to pass through different colored doors. So let's connect the rooms by the doors that are between the 2 rooms. So when we go from the starting point to the beginning of the maze, we're going from room 1 to 2, and we have to pass through a blue door. So we will connect 1 and 2 with a blue colored edge. Where can we go from room 2? We could go to room 6 by passing through a blue door. But we can also go to room 6 by passing through a red door. We can also go to room 3 by passing through a red door. Where can we go from room 3? We could go to room 6 through a red door, or we could go to room 4 through a blue door. From room 4, we can stay in the same room by passing through a red door. This is an important piece of the puzzle. We can also go to room 5 by passing through a blue door.
So he's mentioned that same red door, which is on its own, as an important part of the puzzle. I think that's the key here.
Or we could go to room 7 by passing through a blue door. From 5, we can go to room 6 by passing through a red door. Notice there are 2 red doors, but I will just leave one edge because we can go from 5 to 6 going through either one of the red doors. We could also go to room 6 by passing through a blue door. And from room 6, we can go to room 7 by passing through a red door, or we can exit the maze by passing through a red door. That'll be to room 8. So now let's just focus on this graph that we have created. Our goal is to create a path that goes from room 1 to room 8, and as we pass through another room, we have to alternate edge colors. Now, instead of trying to work from room 1 to room 8 by going through edges of alternate colors, here's another tip. We can work smartly by solving from the end of the maze and going back.
Yeah, so this is what I said. You can actually work backwards from the end of the maze to the start of the maze. I think that reduces the number of possibilities.
Backwards. So let's start from room number 8. From room 8, there's only one thing we can do, which is to take a red edge to room 6. So now we are room 6, and we have taken a red edge. So since the very last move of this puzzle, if it's solvable, is red, we need the second to last move to be a blue edge. So from room 6, we know that the second to last move has to be blue, so it cannot be red. We know that any of these red edges will not be the second to last move.
Okay, so he's drawn the forwards graph, and now he's using the backwards graph to eliminate possibilities in the forwards graph. This is a nice way of doing it. I like this.
Move. So we can just get rid of all these red edges. This is going to eliminate a lot of possibilities. So we can see that from room 6, there are basically two places we could have come from. So one place is room 2, the other place is room 5. Now let's say that the second to last move was coming from room 5. Now what happens when we get to room 5? We've just gone through a blue edge, so now we would need a red edge. But we see there's nowhere that we could go from there. We are stuck here. There's no red edge that goes anywhere else. We've already deleted the edge that was going to 6. That'll just take us in a loop. So we know that this cannot be part of the solution. So we know this is not where you want to go. So we will delete this edge. We now see that 5 is a dead end. We will delete everything going to 5. And we can also easily see that 7 is a dead end. There's no need to go over there. And now we can see the path we need to take. Clearly, we need to go to room 2. From there, we go to room 3. Then the only choice is to go to 4. From 4, we are allowed to circle back to 4 by taking a red edge.
Okay, so that's exactly what I did. I used that single red door on its own to circle round and return along the same path. So that green blob on the bottom right, circling round, going back along those two routes, and then going to the exit.
This allows us to take a blue edge to 3. So we take a red edge to 2, allowing us to take a blue edge back to 1. So we have solved the maze in reverse. In order to work the maze the correct way, all we need to do is flip the arrows to get a path from start to end. So let's go ahead and flip all these arrows. We now have this path. We can overlay it on the original puzzle, and we will now just draw out this solution. We start in room 1, and we take a blue door to room 2, a red door to room 3, and a blue door to room 4. This is where the puzzle gets creative. We take a red door to stay in room 4, which will then allow us to take a blue door to room 3, a red door to room 2.
Okay, so this is exactly my solution. I like this.
Finally, we take the blue door from 2 to 6. Now we've entered 6 with the blue door, so we can exit 6 from a red door, which takes us to the end.
That was kind of awesome. We've made a strong start. We've got the same solution. I like that. I didn't think I would do that so quickly.
Congratulations! We have solved the puzzle. What an amazing solution. Puzzle 2. A library bookshelf has several volumes of an encyclopedia of mathematics shelved side to side as shown. The pages of each volume are 3 centimeters thick, and each cover, front and back, is 0.3 centimeters thick. Assume the same dimensions for all of these volumes. Now, there is a bookworm in the library because nobody is checking out an encyclopedia of mathematics, and a bookworm has gnawed, perpendicular to the pages, from the first page of volume 6 to the last page of volume 7. What is the distance of the bookworm's path?
Okay, so let's try and solve this. We've got this set of books. The pages, collectively, in each book are 3 centimeters thick. Then the covers, the front and the back, are 0.3 centimeters thick. So starting with the information, we're told that we've got these books, and the pages in the book add up to 3 centimeters. And the covers of the book, each cover is 0.3 centimeters. Let's see what that looks like. So if I draw myself a book, here's the book, and let's call that the pages. And then on each side, there's going to be a cover. So there's the cover on that side, and there's the cover on that side. Okay. So the pages are 3 centimeters wide, and each of the covers is 0.3 centimeters. So we've got this representation of a book. Now it tells us that a bookworm has gone through perpendicular to the pages. So if the pages are like this, perpendicular to the pages is the green line. So it's traveling horizontally through the books. So far, so good. And it's gone from the first page of volume 6 to the last page of volume 7. So let's have a look at that. So volume 6 to volume 7. So from volume 6 through horizontally to the end of volume 7. So let's have a read. It says, from the first page of volume 6 to the last page of volume 7. 1 second. Where is the first page on volume 6? Let's think about this. I think that's wrong. I think I've drawn that wrong. The first page on volume 6 is not on the left. If we imagine removing this book from the shelf, where would the first page be if we took it out the shelf, opened it up? In relation to the words on the spine, where would the first page be? I think the first page is on the right, not on the left. On the left, that's the back page. So the first page, I think, is actually here, on that side. I think. Okay, so on my diagram, the first page is here. And then it wants us to go to the last page of volume 7. So I think the same logic applies. The last page of volume 7 is on the left-hand side of volume 7, not the right-hand side. So here's volume 7. And the last page is on the left-hand side. Okay. So those pages are only separated by the covers. There's no pages in between them. It's literally first page, volume 6, volume 6 cover, volume 7 cover, last page of volume 7. Okay, so I don't think we need all of this diagram. To me, it's first page of volume 6, volume 6 cover, volume 7 cover, and then last page of volume 7. So they're only separated by the covers. If we know that covers are 0.3 centimeters thick, this is 0.3 and this is 0.3, collectively it's 0.6 centimeters. I think that's the answer. I'm not sure if I'm right though. Let's see if I've got it correct.
So this puzzle tricks a lot of people, and let me illustrate the wrong way that most people think about the problem at first. So we have volume 6 and 7. When most people read that you're going through the first page of volume 6 to the last page of volume 7, intuitively you're going to be traveling a distance that's almost equal to the length of the two volumes.
This is what I did initially. I thought it was from the left of 6 to the right of 7, so it goes through the whole book. But I think I'm right, because if he's saying that this is intuitively wrong, but I think I'm right, because he said that this is wrong. Let's see.
But you're going to be excluding some covers. When most people read that you're going through the first page of volume 6 to the last page of volume 7, intuitively you're going to be traveling a distance that's almost equal to the length of the two volumes.
So this is what I did initially. And this is why I changed my answer, because I thought this was wrong. And he's saying it's also wrong, so hopefully I've got it right. Let's see.
But you're going to be excluding some covers. You're excluding the front cover of volume 6, but you are going through the pages of volume 6. You are then going through the back cover of volume 6 and the front cover of volume 7, and you are then going through the pages of volume 7. So most people think the answer would be something like 2p plus 2c.
Yeah, that's what I was doing first. But I think that's wrong, and I think I've got it right. But let's see what he says.
The pages have a thickness that are 3 centimeters thick, so p is equal to 3, and each cover, front and back, is equal to 0.3 centimeters, so c is equal to 0.3. Substitute in to this expression, and we have 2 times 3 plus 2 times 0.3, and this simplifies to be 6.6 centimeters. And that's what most people think when they read the puzzle at first. But this is incorrect.
Yeah, I thought it was incorrect too. Hopefully I'm right. Let's see.
The problem is we have the totally wrong perspective on what it means to go from the first page of volume 6 to the last page of volume 7. We're usually reading books in our hands, and we don't have a clear understanding of the distances when books are put on a shelf. So what is the correct answer? We need to think about it carefully. So let's look at volume 6. The very front of the book will be on the right side, and the back of the book will be on the left side. So the book will go from right to left.
So yeah, this is exactly what I was saying. If you took the book off the shelf, where is the front of the book and where is the back in relation to the words on the spine? So I looked at the words on the spine and I thought, hey, the top of those words is the front of the book. So the front is on the right. And the bottom of those words is the back of the book. So the back is on the left.
So the first page of volume 6 will be right in the middle of this diagram. That will be the
Okay, I think I've got it right. I think I'm sure that I'm right. Let's see.
front of the book, and that's where the first page will be. Now let's think about the last page of volume 7. Volume 7 is also read from front to back in this manner, and the back of volume 7 is going to be right in the middle of this diagram as well. So we only need to calculate this distance from the first page of volume 6 to the last page of volume 7.
So yeah, the only space between those was the covers. There's no pages between them. I think I'm right.
So this distance will be equal to what? It will only be equal to the amount of the cover of volume 6 and the cover of volume 7. So we need to add the front cover of volume 6 and the back cover of volume 7.
So yeah, it's just the two covers, exactly what I did. The cover of volume 6, the front cover of volume 6, and the back cover of volume 7. They're both 0.3 each, so 0.6 in total.
So this distance will be equal to c plus c, which equals 2c, and that will be equal to 2 times 0.3, which equals 0.6 centimeters.
So I can pat myself on the back. I got it right. Luckily, I nearly got it wrong.
Amazing. Puzzle 3.
Okay, so now we're on to puzzle 3. Hopefully this is going to get a little bit more difficult. I'm liking this so far, though.
There are 3 people in this puzzle. We have Alice, Bob, and Charlie.
Okay, I think I know where this puzzle's going to be going. This is a very common, are they lying, are they telling the truth, I think, from looking at that picture.
Each of them is a finger pointer. Alice says that Bob is lying, Bob is saying that Charlie is lying, and Charlie is saying that Alice and Bob are both lying. Logically, who is lying and who is telling the truth? Assume that each person is either a truth teller that always tells the truth, a liar that always says lies, and everyone knows each other's type. And no one is uttering a joke or a sarcastic statement.
So we've got Alice, Bob, and Charlie. Alice is saying Bob is lying. Bob's saying Charlie is lying. And Charlie is saying that Alice and Bob are both lying. And we got to work out who's telling the truth and who's lying. We do know that each person is either somebody that's telling the truth, and they always tell the truth, or somebody that's lying and they always lie. So nobody's joking. And also, everybody knows about everybody else. So Alice knows about Bob and Charlie. She knows whether they lie or tell the truth. Same goes for Bob, he knows about Alice and Charlie. And the same goes for Charlie, he knows about Alice and Bob. So there's no sarcastic statements, there's no jokes, there's nobody that's confused. This is a very direct question. So I think with this one, I'm going to start with Alice. And let's assume that Alice is telling the truth. So Alice says Bob is lying. So Bob must be lying if she's telling the truth. Bob says Charlie is lying, and that's a lie. So we'll write Bob as a liar because Alice, who tells the truth, has said Bob is lying. So Bob is lying. When Bob says Charlie is lying, that's a lie. So Charlie must be telling the truth. If Charlie's telling the truth, then both Alice and Bob must be lying. But Alice isn't lying. We started with Alice telling the truth to get to Charlie telling the truth. And both of those statements can't be correct. So let's erase all that and let's see what happens if Alice is a liar. So Alice is now pointing at Bob saying Bob is lying. But she's lying herself. So Bob is not lying. Bob is telling the truth. What truth is Bob saying? Bob is saying that Charlie is lying. And that must be the truth because he's a truth teller. Is Charlie lying? Charlie says Alice and Bob are lying. Is that the truth or is that a lie? That's a lie, so I think this works. Alice is lying, Bob is telling the truth, and Charlie is also lying. Let's see if I've got it right.
Let's work through it logically. Let's suppose that Alice is telling the truth.
So he's basically done exactly what I did. He started with saying one of the people is telling the truth. And I started with Alice. He started with Alice as well. We assume that she's telling the truth.
In that case, Bob is lying, which means Bob's statement that Charlie is lying is wrong. Therefore, Charlie must be telling the truth. But if Charlie is saying that Alice and Bob are lying, that contradicts the assumption that Alice is telling the truth.
Exactly. If Charlie's telling the truth, then Alice cannot also be telling the truth. They're both contradictory.
There is no way that Alice could be telling the truth and we don't end up with contradictory logic. This cannot be true. Now, let's consider that Charlie is telling the truth.
Okay, so he's done it slightly differently here. I walked it all the way back to Alice, and I switched her from telling the truth to telling a lie, and I did the whole thing again. Let's see if it works out the same.
In that case, Alice and Bob must both be lying. But then Alice's statement that Bob is lying would be a true statement, and that contradicts the fact that Alice is lying.
So this is basically saying the same thing again, that Charlie and Alice can't both be making true statements.
So once again, we have a contradiction, and it's not possible that Charlie is telling the truth. So the only possibility is that Bob is telling the truth. Let's make sure there are no contradictions here. If Bob is telling the truth, Charlie's statement will necessarily be false as Bob is telling the truth. Alice saying Bob is lying will also be a false statement as Bob is telling the truth. Therefore, Bob is telling the truth, and Alice and Charlie are lying.
Okay, so I think that's exactly the same as what I got. Bob is telling the truth, Alice and Charlie are lying. Bob is telling the truth, he's a truth teller. Alice and Charlie are both liars. I did it slightly differently, that I worked from Alice, made her true, worked through the logic, found it didn't work, then worked all the way back to Alice, made her false, made her a liar, and then worked through the logic and it fit, which I believe was a little faster.
And that's the answer. Puzzle 4.
Okay, we're on puzzle number 4 now. Let's see how this one goes.
We have matchsticks arranged in the shape of 5 squares in an L shape. The challenge is to move 2 sticks to make 4 identical squares.
Okay, so this one's rather interesting. I don't know how to do it. We have to move 2 sticks to make 4 identical squares. We've got 5 squares at the moment. 4 identical squares, so they all have to be the same size. I was wondering if we could make like 1 big square and 3 small ones, but they have to be identical. So they all have to be the same size. I'm not sure. Okay, so let's try moving some and see what happens. So I'm going to start by moving this one to here. That gives us a rectangle. It's not good. It's not good at all. It says 4 identical squares, not rectangles. Okay, so we can't really move that. We need to move 2 sticks to make 4 identical squares. Okay. I'm not sure about this one. If I move this one, I still have a rectangle. It's not a square. It needs to be an identical square, not a rectangle. How about this one? If I move this here, then I move this here. I still don't have a shape. It's some weird L shape. I'm not so sure about this question. Move 2 of the sticks to make 4 identical squares. I'm wondering if there's some kind of trick to this where you gotta stand them up and make them 3D or something. But how would that work if you're only moving 2? And can you fold the page? Oh. Oh, wait. Okay. Wait, I think I've got it. 4 identical squares. If I do this one and this one, I still have 5. I still have 5. It says I have to have 4. Does it say exactly 4? I've got 4. I've got 1 extra. I don't know. I don't know. That doesn't sound correct either. I think I might have it. I think I've worked it out. I think. Like, if I erase this matchstick from here, And if I put that matchstick over here, so far so good. Now if I erase this matchstick from here, and I put that matchstick here, I think I have 4 identical squares. Oh my god, that was more difficult than I assumed. 1, 2, 3, 4 identical squares. That's an interesting question. Let's see if I've got it right.
It is said that children solve this much easier than adults.
Not sure if I should take offense to that.
So how can you figure it out? Most adults think about the problem like this. They look at the word move and they think that the word move could also be interpreted as the word remove. So
yeah, this is what I was doing originally. I figured if maybe we could get rid of 2 of the matchsticks, like just remove them. So the 2 in the bottom right, if I remove those, we would have 4 identical squares. But it doesn't say remove, it says move. So they do have to be moved and kept in the shape somewhere.
They take these 2 sticks that are in the corner and they just remove these 2 sticks. And
exactly what I was thinking originally, but I did change it. Let's see if he does it my way.
they say, look, I have made 4 identical squares. I am so clever. Now this is one possible creative solution to the puzzle. However, it's not exactly what's intended because the puzzle doesn't say to remove 2 sticks, it says to move them. So let's try to rearrange the 2 sticks so that they're part of the final puzzle. So how can we move 2 sticks? We will still have a shape that uses all of these sticks, and we will make exactly 4 identical squares. Let's think about it logically. So if you have a square made out of matchsticks, you will need to use exactly 4 different sticks. Now, how many matches are in the original arrangement? Let's go ahead and quickly count up these matchsticks, and we will see that we have a total of 16 matchsticks. Now, our goal is to make 4 identical squares. If you multiply that by 4 sticks per square, that'll exactly be 16 sticks. So if we want to rearrange 16...
So what he's saying here is that none of the squares can share a side, because that will remove one of the matchsticks. Like each square, all 4 sides cannot be attached to another square. They have to be separate from each other. So they're going to be attached on the corners, but they can't share a side. I think that matches my drawing. Like none of my squares share a side. They share corners. So each square has its own 4 sides, which makes a total of 16 matchsticks.
16 sticks into 4 identical squares. This is only possible if each stick is on its own square.
So yeah, that's exactly what I just said. Hopefully I'm going to get this right.
None of the squares will share a common side. Now in the original arrangement, some of the squares are clearly sharing a common side. So let's take a look at these 2 squares. We clearly are sharing 1 stick for 2 of these squares. So imagine we want to have 4 squares that have no common sticks. So let's say we take this square and we leave it be, and we need to somehow remove one of the matches from this square that's next to it so that we don't have 2 squares sharing a common stick. Now the same thing can be true in the bottom arrangement. Here we have 2 squares that are sharing a stick. So if we want to keep these 4 sticks to be 1 square, we know that we'll have to remove one of these 3 sticks and move it somewhere else in this arrangement. So now by symmetry, we can just consider pairs that are corresponding to each other. So let's get started. Suppose we take these 2 sticks. Now imagine we move them somewhere away. Is it possible?
So this is what I did originally. I tried to move those 2. I flipped them over and I used them the other way around. which gave me a very strange L shape, which again is not a square as it says.
Possible that we could place them somewhere around the remaining sticks and we end up with 4 identical squares? I don't see it. So we will eliminate this possibility. Now let's look at another possibility. Let's take a look at another pair of matches that are symmetrical. So let's take a look at these two. Let's imagine we're going to move them around somewhere else. Well, here's the arrangement that remains. I don't really see any clear way that we could put these two matches to get 4 identical squares. So we will eliminate this possibility as well. So that leaves only one more pair to consider. So let's take these two matches.
So yeah, the same matchsticks that I moved in my solution. Let's see if he puts them in the same place that I did.
Matches which are on the middle. And let's imagine we move them out. Now we are left with exactly 3 identical squares, and there's exactly one spot where we could create a square. All we need is 2 more sticks. So voila, we go ahead and put these.
So yes, exactly my solution. I'm happy that I got that right. There it is. I got it right. I'm very happy.
These 2 sticks over here, and we have created 4 identical squares by moving 2 sticks. So this will be the solution. We have moved 2 sticks to create 4 identical squares. Wow. Puzzle 5.
Okay, puzzle number 5. Let's see what this one's got in store for us.
There are 3 different keys and 3 different doors with locks. Each key opens a different door. Unfortunately, the keys are mixed up, and you need to label them so that you know which key opens which door. In how many attempts, in the worst case, can you be sure you can identify all 3 keys? Let's work through this logically.
We've got these keys, we've got these doors. Each key opens a different door, but we don't know which one. We got to figure out how many attempts in the worst case scenario that we can take to identify which key matches with which door. So let's try best case scenario. So best case scenario, we try a key, it works. We try the next key, it works. And then we've got the final key, which we know works on the last door. That's the best case scenario. What's the worst case? So I think worst case scenario is, let's start with this blue key. We're going to try the blue key in the yellow door. Worst case scenario, it does not work. So it's not blue. Then we try it in the orange door. Worst case scenario, it doesn't work. So we've taken two attempts. I don't think we need to try it in the grey one. Because if we know that all 3 of these keys work on these doors only, if the blue one doesn't work in the yellow or the orange, we can infer that it must work in the grey. So we've taken 2 attempts, and we've inferred that the blue goes in the grey door. Okay, so now we need another key. Let's try the green one. And we're going to try that in the yellow door. Again, worst case scenario, it does not work. That's 1 attempt. The grey door is already done, because the blue key belongs to it. So we can't use the grey door again. We've only got 1 door left. And again, we don't need to try it because there's only 1 door left. So we know it works here. That's 1 attempt. And the last one, the orange key, we don't need to try that because we know that there's only 1 door left. So we can infer that that's the only door that the orange key must belong to. We don't need any attempts. So I think, worst case scenario, we need a total of 3 attempts. Let's see if that is the correct answer.
Let me label the 3 keys as B, G, and Y. Let me label the 3 doors as 1, 2, and 3. So here's some notation. Suppose I write B, G, Y. That will be a solution in which B opens door 1, G opens door 2, and Y opens door 3.
Okay, so this is a very interesting way of doing it. Let's see which way he takes this. I do like this. I think he's going to use elimination to eliminate some of them based on the letters.
So how many different possibilities are there? Well, this will exactly correspond to the number of permutations of 3 items, which is 3 factorial, which equals 3 possibilities for door 1, then 2 possibilities remaining for door 2, and 1 possibility for door 3, which will be 3 times 2 times 1, which equals 6 possibilities. We have BGY, BYG, GBY.
Okay, so he's writing out all the options. You can have the blue key, green key, yellow key, or you can do blue key, yellow key, green key. I think this is a very long way of doing it, but we'll see.
Y, GYB, YBG, and YGB. Now, the amazing thing is we don't actually need to test all 6 different possibilities.
So he's given us the answer there that we can identify which key belongs to which door in 3 attempts, which I think is exactly what I got. 3 attempts. I think my way was a little easier. They are both mathematically similar, but mine used a more inference method rather than elimination.
The remarkable answer to this puzzle is we can identify the keys in just 3 attempts. So how can we do that? Let's suppose that we start by testing the key B on door 1. Now we're looking for the worst possible case. So it is possible that this key does not work on door 1. So let's say that.
So exactly what I said, we take the first key, the blue key, and try it on the yellow door. And worst case scenario, it doesn't open. So that key is not for that door. So what he's going to do now, I think he's going to eliminate the 2 possibilities which have B as the first letter, because B doesn't belong to the first door. I think. We'll see.
That this is not going to work. So when we look at the 6 possibilities, we can eliminate the very first 2 because we know.
There it is. Yeah, we're going to eliminate those 2 because that key does not belong to that door. Slightly different to how I've done it. I prefer my method because I'm inferring things rather than using elimination on the whole set.
That B will not work on door 1. So now let's put this to the side and suppose that we test G on door 1. Now we're looking for the worst case, so it is possible that G also doesn't work on door 1. We can then eliminate 2 more possibilities, GBY and GYB. But now here's the interesting part. We know that B and G don't work on door 1, so we must be sure that Y will work.
So this is very slightly like the other way round to the way I did it. I did blue key to yellow door, then blue key to orange door, and then I didn't need to do blue key to grey door because I know that that's the only one left, so I can infer that that one works. He's done it the other way around. He has done blue and green to door 1, so he's inferring that the yellow belongs to door 1. It's the same method, but he's taken a different approach to it.
Work on door 1. So we already know that Y works. We don't need to actually test it out on door 1.
It's exactly what I said about the blue key to the grey door. We don't need to test it. If it's the only door left, we can infer it. For him, he's saying it's the only key left, so he can infer it. Same method, different perspective.
There are only 2 possibilities remaining, which is YBG and YGB. So we need to differentiate between those 2. So let's go ahead and see whether B or G is working on door 2. So let's test B to door 2. So if we put B to door 2, suppose in the worst case that this does not work, in that case we would know that B doesn't work for door 2, it must work for door 3, and G must work for door 2. But now we have identified which possibility works. We know it must be YGB. We have used exactly 3 tests to do this. Therefore, after 3 tests, we can be sure.
Exactly. So worst case scenario, 3 tests, 3 attempts will get you the answer.
We have identified all 3 keys. We don't need to work through all 6 possibilities. We can have that so that we just figure it out in 3 different tests. Incredible. Puzzle 6.
5 out of 5 so far. Let's see if we can get puzzle 6 correct.
Here's a geometrical figure. You could call it a leaning tower. The puzzle will be to solve for the area of this square at the top of the diagram. But let me define this diagram a bit more clearly. So at the very base of this figure, we have 5 different isosceles triangles, and all of their bases are aligned.
So I think that's important, that they're isosceles triangles.
So each of these triangles is isosceles. The very bottom is the base, and we have the 2 sides that are not the base will be equal to each other. The bases have lengths of 12, 13, 14, 15, and 16 centimeters. Now, on top of these triangles, we have rhombuses, or rhombi. Now, each of these 10 different quadrilaterals is going to be a rhombus. So what exactly is a rhombus? It's a quadrilateral that has all 4 sides that are equal to each other, and it's a type of parallelogram, so opposite sides will be parallel to each other. Now, the very top rhombus is actually a special case. It's going to be a square. And the challenge is figure out the square's area. This is a truly wonderful geometry puzzle, and I admit that when I saw it, it stumped me. But when I read the solution, it was so beautiful, I just had to share it.
Okay, so we've got that square, we've got a bunch of rhombi underneath it, and then at the end we've got some isosceles triangles. And we've got to work out the area of that square. Okay, I'm going to be honest, this isn't immediately obvious to me. So what do we have? We have isosceles, 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 another isosceles, and a final isosceles. So all those triangles at the bottom are isosceles. But they've all got different bases, so they're all different to each other. And then we've got a bunch of rhombi. What we know about rhombi is all the sides are the same length. So the isosceles triangles, the 2 sides, which are the same on the isosceles triangle, also match with the rhombus which they're connected to. I think that's important. So if this one's the green one, then this also has to be green. Those are all the same, which makes all of these the same. Okay, which makes all of these the same length, because it's an isosceles at the bottom, so both sides on the isosceles have to be the same. Therefore, all of these are the same, because that's a rhombus. Okay. Let's keep going. So these are the same, and these are the same, and so are these, and so are these, and so are these. Okay, so I've drawn a bunch of lines, and all of those sides, each side that has a line is the same length as every other side that has a line. Okay, so I think I'm noticing something. I'm noticing that this line here, let's do it in a different color, that this line here is the same as this line here. And they are the same as these lines here. Okay. So let's draw those. Let's start with the square. So there's my square, which is at the top of the shape. Now I've got 2 isosceles triangles at the bottom of the shape, but the sides are the same length. And there it is. Obviously my drawing is not super accurate. We also know that this length is 12, and this one is 16. And this is all we know so far. And we have to try and work out the area of that square. I'm not sure how to do this one. We've got the 12, we've got the 16, and we're trying to work out the area of the square. I'm not entirely sure. I've got 2 isosceles triangles. got a square. Okay, I think I'm going to start with the isosceles triangles. Let's make them a bit bigger. Let's also join them all together. And we'll change the color of one to make it easier for me to identify them. So let's start with the red one. It's an isosceles triangle. So if we drop a vertical line down the middle, say we cut it in half, we create two right angle triangles inside the red one. This one's got a width of 6, so is this one, because it's right down the middle. Let's do the same on the other one. So these would have a width of 8. So now what we've got is we've got right angle triangles inside the isosceles triangles. We also know that that blue one is a square, so this must be 90. Two right angle triangles. Is this congruency? This side is the same as this side. So we have a right angle, which is the same in both. We also have the hypotenuse, which is the same in both because they are both sides of the square. And if they're both sides of a square, they have to be the same. So, okay, also, this angle here and this angle here. Okay, so we've got that straight line with 180 degrees. And we know the blue angle is 90 degrees because it's inside the square. And then the pink and the orange angle must add up to 90. Therefore, this has got to be the same as the orange angle. And this has got to be the same as the pink angle. These are congruent triangles. So if one side is 6, and if they're congruent, it means they're the same. The other side has to be 8. That also has to be 6. And I think now we can do Pythag to work out the hypotenuse. So 8 squared plus 6 squared equals the hypotenuse squared. So we square root it. So it's hypotenuse, so we'll call it C squared equals 8 squared plus 6 squared. 8 squared is 64, 6 squared is 36, therefore c squared is 100, and if c squared is 100, c is 10. Each side of the square is 10, therefore the area of the square, I think, is 100, cm squared. Okay, so let's see if I've got it right. I'm not sure about my answer, but we'll see if I've got it correct.
So let's work through this problem step by step. We will start out by defining the side length of the square to be equal to x. Since we have a square, all 4 sides will have the same length. Also, all 4 angles will be right 90-degree angles. Now in a square, we have all 4 sides equal, so these 2 sides are equal. Now we have 10 different rhombi, and we know that all of the sides will have the same length, and opposite sides will be parallel. So in the square, this side will be parallel to this side. Now, as we go to the next rhombus, we know that we will have the same side length for all 4 of these sides, and opposite sides will be parallel. So we can continue this to the next rhombus. We'll have the same length, and then opposite sides will be parallel, and that will continue down to one of the sides of this isosceles triangle, which is also a side.
That's exactly what I said, that the isosceles triangle, one of the sides is the same as one of the sides of the square. And because squares have all the sides the same, so do rhombi, then the other isosceles triangle on the other side must also have the same length. So both isosceles triangles, the sides are both the same.
Side of the rhombus, this length will be equal, and this side will be parallel to the opposite side. So let's take a look at this length of the square. So we can then just translate it to the opposite side of the rhombus. We know that it'll have the same length x, and it will be parallel. We translate it to the next opposite side of the next rhombus. It'll have the same length, and it will be parallel. And finally, this goes down to this side of this rhombus, which is a side of this isosceles triangle, and we know it will have the same length x. And let's just note that this yellow line segment will be parallel to this side of the square. Now let's work an adjacent side of the square. So let's mark this line segment. Now we know.
So I kind of did the same thing, but I worked upwards rather than downwards. It's the same Same method, but just a different perspective.
We know that opposite sides will be parallel, and all four sides of a rhombus will be equal to each other. So we can just translate this length to the opposite side of the rhombus. We know that we have a parallel line segment and it will have the same length x. And we know that this line segment will have the same length x and it will be parallel to this side of the square.
So that's also something that I found, that both of the isosceles triangles have the same sides because they relate to the square. And the square has all the same sides.
But now let's take a look at the two adjacent sides of the square. We have this yellow side here, and we have this orange side, and we know in a square, the two adjacent sides will meet at a right angle. They will be perpendicular to each other. So we know at the base of the diagram, this yellow line segment must be perpendicular to this orange line segment. And amazingly, that's the key detail we're going to need to solve this puzzle. So remarkably, we can actually get rid of all these intermediate edges. We can just vanish a lot of this tower. So we can go ahead and remove all of these intermediate edges of all of these rhombi. We don't need these to figure out the area of the square. And remarkably, this whole diagram is going to collapse quite incredibly. We can also get rid of these isosceles triangles in the middle. We don't need them at this point. So now let me just collapse the diagram. Let me move this right triangle and connect it to this left triangle.
It looks like he's drawing the same diagram that I drew, which is the square with the two triangles either side of it.
And we know that these two edges meet at a right angle. We need to figure out the area of the square, which will be equal to x squared. So let's do this just by looking at these two triangles. Let me just power them up and magnify them. So now we have two lengths of x that meet at a right angle, and we have two isosceles triangles. Let's drop an altitude from each of them. So let's drop an altitude from the triangle of 12 centimeters.
This is the vertical line that I created in my triangles. So I dropped a vertical line between both triangles to break the isosceles into two right-angled triangles. He's done the same thing. He's called them an altitude, which is a nice word for them. I think I'm going to use that from now on.
This will divide the base in half so that it will have a right angle, and we know that each length will be equal to 6. Let's drop an altitude to the base of this other isosceles triangle. We know it'll meet at a right angle, and the base will be split in half, so we have 8. Now let's label this acute angle as blue and this acute angle as green. Now this blue plus the right angle plus this green will be equal to a straight line.
That's the same thing I said. That middle angle there, in my case, is the pink angle, the orange angle, and the blue angle add up to 180. So the pink and the orange have to be 90 because the blue is a corner of a square, which we know is 90.
So we have blue plus green plus 90 degrees is equal to 180 degrees. Subtracting 90 degrees from both sides of the equation, we have that blue plus green is equal to 90 degrees. In other words, the blue and green angles are complementary. So we have two right triangles. We know that they have complementary angles, which means they will be similar, but we know the hypotenuse has the same length. Therefore, these two right triangles will be congruent to each other.
Exactly the same thing I found, that they are congruent. And same reason that they are complementary, that the blue has a green above it, and the green has a blue above it, in his case. Where the hypotenuse are the same, you got a 6, you got an 8. So the verticals have to be 8 and 6.
So where we have a base of 6 here, we know that the altitude will be 8, and in the other triangle, we have a base of 8, and the altitude must be...
Again, exactly what I found, that the altitude, the vertical line of the triangle which has a base of 6, the altitude, the vertical line has to be 8. And the base is 8, so the altitude, the vertical line has to be 6. And I assume now he's just going to do Pythag, but we'll see.
Must be equal to 6. So we have a right triangle, and we know we can solve for the hypotenuse. we have x squared is equal to 6.
Okay, cool. So the same method that I used, Pythagoras' theorem, a squared, b squared, c squared. 8 squared plus 6 squared equals the c squared. In his case, he's used the letter x, so x squared.
X squared plus 8 squared, and that is exactly equal to 36 plus 64, which equals 100. So we know the area of the square is 100 square centimeters.
So yeah, that's something that I didn't need to do. I square rooted it and then squared it again. That wasn't required because we know that the square is the sides squared. So we didn't need to square root it. We've already got the squared version.
And like magic, we have figured out this puzzle. The area of the square is 100 square centimeters.
The square there is 100 centimeters squared. I'm kind of pleased with myself that I got that one. That was actually a very difficult question. So these videos are actually quite great. I like these videos. I like trying these puzzles. I really enjoy them. Sometimes I get them wrong. This one, luckily I've got 6 out of 6. I will be doing some more of these, so let's see if I continue to get them right.